Welcome to the third lecture video in our Class 16 series of lecture videos. This one will hopefully be a little bit shorter than the prior two, but we'll make it up on the last two. I guess it gives you a bit of a respite from focusing in on these videos for this particular class series. So conformations can play a role in olefin-alkene geometry. We discussed bimolecular elimination, and we saw that the transition state preferred an anti-paraplanar conformation for pulling the beta carbon hydrogen off of our molecule to kick out the leaving group from our alpha carbon. Here we've got an interesting molecule that contains a couple of methyl groups, even a phenyl group or a benzene ring. And we've drawn this particular stereoisomer in such a way that we've got the carbon leaving group bond in the plane. We could rotate freely around this carbon-carbon single bond such that we put this hydrogen, beta carbohydrogen, in an anti-paraplanar sense as drawn on this bond line conformation for the molecule. Now, if we add sodium methoxide, which is a fairly strong base, just like hydroxide and methanol, we're going to do an E2 reaction. We're not going to let this have time to fall apart and do SN1. We're under basic conditions. We're not really going to tolerate carbocations. And if we do that, if we pull this hydrogen, this proton, off of this beta carbon and form a double bond between the beta carbon and this alpha carbon and kick the mesylate group out, we notice that this benzene ring and the methyl group, which both have wedged bonds, they end up on the same side of the resulting alkene. Similarly, this proton, hydrogen, and this methyl group that both have dashed bonds, they also end up on, the same relative side as that alkene. If we were to turn this alkene bond line diagram and put it in the plane, we see that our preferred product has this benzene group opposite a methyl group and this methyl group opposite a hydrogen atom that has not been explicitly drawn. So what if instead we rotated around this carbon-carbon single bond and put our molecule in the syn paraplanar transition state for this E2 reaction? We remember that we did not prefer the syn paraplanar transition state, but if the reaction happened through the syn paraplanar transition state, now the two methyl groups would be on the same side of the alkene. They would be cis to each other, and that phenyl group and this hydrogen would be cis to each other. But this is not the product that we get out of this reaction. We prefer the anti-paraplanar transition state. And so it gives us a specific alkene geometry as opposed to another possible choice arising from the syn paraplanar conformation. So this is difficult to understand, but as we pluck this proton off and this mesylate leaving group leaves in the anti-paraplanar transition state, this methyl group comes down, this hydrogen comes down as the p orbital lobe on top starts to grow, and this carbon transitions from sp3 hybridization to sp2. Similarly, for the back carbon, the p orbital lobe pointing straight down begins to grow, and the methyl group moves up as well as the benzene group moving up. And so the benzene group ends up eclipsing the methyl group. Similarly, the hydrogen ends up eclipsing this methyl group, and we get our preferred geometry alkene, which we saw up here. It's just flipped over. In the syn paraplanar state, here's a Newman projection of our methoxide plucking off this proton. We would kick out our mesylate leaving group, and now this methyl group and this methyl group would come down into the plane, and the benzene group and the hydrogen would come down into the plane, and we would get this alkene geometry. And so here it is, the other possible alkene geometry that we showed for this reaction that was not preferred. So I think that pretty much does it for this particular lecture video. If you have questions on this, please remember to ask me during the class time. This is, fairly subtle and advanced to understand in terms of, the mechanism that we're talking about by molecular elimination and how those p orbitals that go to make up the pi bond start growing in such a way to push certain groups into coplanarity. So I'll see you at the class time eventually, but I guess you have a couple more videos in this series to watch before we're done.